Java method overloading. Method overloading in Java is a feature that allows a class to have more than one method with the same name, but with different parameter lists. These differences can be in the number of parameters, the type of parameters, or the order of parameters. Method overloading improves code readability and reusability by enabling multiple ways to perform similar operations using a single method name. Key points of method overloading. Same method name. All overloaded methods must have the same name. Different parameter list. Overloaded methods must differ in the number, type, or order of parameters. Return type. The return type of overloaded methods can be different, but the return type alone cannot be used to differentiate methods. Examples of method overloading. 1. Overloading by changing the number of parameter. Public class calculator. / method to add two numbers. Public int add, int a, int b. Return a plus b. / overloaded method to add three numbers. Public int add, int a, int b, int c. Return a plus b plus c. Public static void main, string args. Calculator equals new calculator. Int sum1 equals calculator.add, 10, 20, / calls the first add method. Int sum2 equals calculator.add, 10, 20, 30, / calls the overloaded add method. System.out.println, sum of two numbers, plus sum1. System.out.println, sum of three numbers, plus sum2. Output. Sum of two numbers, 30. Sum of three numbers, 60. 2. Overloading by changing the type of parameters. Public class display. / method to display an integer. Public void show, int number. System.out.println, integer, plus number. / overloaded method to display a string. Public void show, string text. System.out.println, string, plus text. Public static void main, string args. Display equals new display. Display.show, 100, / calls the first show method. Display.show, hello, / calls the overloaded show method. Output. Integer, 100. String, hello. 3. Overloading by changing the order of parameters. Java. Copy code. Public class printer. / method to print an integer and a string. Public void print, int number, string text. System.out.println, number, plus text, plus text. / overloaded method to print a string and an integer, order changed. Public void print, string text, int number. System.out.println, text plus number, plus number. Public static void main, string args. Printer equals new printer. Printer.print, 50, Java, / calls the first print method. Printer.print, Java, 50, / calls the overloaded print method. Output. Number, 50, text, Java. Text, Java, number, 50. Method overloading and type promotion. When the data types of arguments differ, Java may promote smaller data types, like byte, short, or char, to larger data types, like int or long, to match an available method signature. This is called type promotion. Example with type promotion. Public class type promotion. Public void display, int a. System.out.println, method with int argument, plus a. Public void display, AA. System.out.println, method with double argument, plus A. Public static void main, string args. Type promotion TP equals new type promotion. TP display, 5, / calls the method with int argument. TP display, 5.5, / calls the method with double argument. TP display, A, / A is promoted to int, ASCII value of A is 65. TP display, 5L, / calls the method with double argument, because there is no method with long argument, and long can be promoted to double. Output. Method with int argument, 5. Method with double argument, 5.5. Method with int argument, 65. Method with double argument, 5.0. Explanation. Display, the character A is promoted to its ASCII value, 65, so the display, int A, method is called. Display, 5L there is no method with a long parameter, so the long value is promoted to double, and the display, double A, method is called. Method overloading and autoboxing. Autoboxing is the automatic conversion that the Java compiler makes between primitive types and their corresponding object wrapper classes, example int to integer. Method overloading can take advantage of autoboxing. Example with autoboxing. Public class autoboxing. Public void show, integer A. System.out.println, method with integer argument, plus A. Public void show, double A. System.out.println, method with double argument, plus A. Public static void main, string args. Autoboxing ab equals new autoboxing. Ab.show, 100, / int is autoboxed to integer. Ab.show, 50.5, / calls the method with double argument. Output. Method with integer argument, 100. Method with double argument, 50.5. Method overloading versus method overriding. Method overloading occurs within the same class and allows different implementations of a method based on different parameter lists. Method overriding occurs between a superclass and a subclass, where a subclass provides a specific implementation for a method already defined in its superclass. Conclusion. Method overloading is a powerful feature in Java that allows you to create flexible and intuitive APIs by using the same method name with different signatures. It improves code readability and provides different ways to handle various inputs within the same method name. 2. Java scope. In Java, scope refers to the region of the program where a variable or method is accessible. Understanding scope is crucial for managing the visibility and lifetime of variables and methods in your code. Java has several levels of scope. Local scope, or block scope. Instance scope, or object scope. Class scope, or static scope. Method scope. 1. Local scope, or block scope. Local scope refers to variables declared within a method, constructor, or block, example within braces. These variables are only accessible within the block where they are defined and are not visible outside of it. Example of local scope. Public class example. Public void display. Int local variable equals 10, / local variable is accessible only within this method. System.out.println, local variable, plus local variable. Public static void main, string args. Example equals new example. Example.display. / uncommenting the following line will cause an error because local variable is out of scope. / system.out.println, local variable. Explanation. Local variable is declared within the display method, so it's only accessible within that method. 2. Instance scope, or object scope. Instance scope refers to variables, fields, that belong to an instance of a class, i.e., an object. These variables are also known as instance variables or fields. Each object of the class has its own copy of the instance variables, and they are accessible as long as the object exists. Example of instance scope. Public class example. / instance variable. Int instance variable. Public void display. System.out.println, instance variable, plus instance variable. Public static void main, string args. Example 1 equals new example. Example 1 dot instance variable equals 5. Example 1 dot display, / outputs, instance variable, 5. Example 2 equals new example. Example 2 dot instance variable equals 10. Example 2 dot display, / outputs, instance variable, 10. Explanation. Instance variable is accessible by any method within the class. Each instance of example has its own instance variable. 3. Class scope, or static scope. Class scope refers to variables and methods declared with the static keyword. Static variables and methods belong to the class rather than any specific instance. They are shared among all instances of the class and can be accessed without creating an object. Example of class scope. Public class example. / static variable. Static int static variable. Public static void display. System.out.println, static variable, plus static variable. Public static void main, string args. Example.static variable equals 10. Example.display, / outputs, static variable, 10. Example 1 equals new example. Example 1 dot static variable equals 20. Example.display, / outputs, static variable, 20. Example 2 equals new example. Example 2 dot static variable equals 30. Example.display, / outputs, static variable, 30. Explanation. Static variable is shared by all instances of the example class. Changing its value in one instance affects the value across all instances. 4. Method scope. Method scope refers to the scope of a method itself. A method can access class variables, both static and instance variables, and local variables defined within its own body. However, methods cannot directly access variables defined in other methods. Example of method scope. Public class example. Int instance variable equals 5. Public void method 1. Int local variable equals 10, / local to method 1. System.out.println, instance variable, plus instance variable. System.out.println, local variable in method 1, plus local variable. Public void method 2. / local variable from method 1 is not accessible here. / uncommenting the following line will cause an error. / system.out.println, local variable in method 1, plus local variable. Int local variable equals 20, / local to method 2. System.out.println, local variable in method 2, plus local variable. Public static void main, string args. Example equals new example. Example.method 1. Example.method 2. Explanation. Local variable in method 1 is not accessible in method 2, and vice versa. Each method has its own scope for local variables. Shadowing. Shadowing occurs when a variable declared within a certain scope, example a local variable, has the same name as a variable in an outer scope, example an instance or class variable. The variable in the inner scope shadows the outer variable, making the outer variable inaccessible within the inner scope. Example of shadowing. Public class example. Int x equals 10, / instance variable. Public void display. Int x equals 20, / local variable shadows the instance variable. System.out.println, local x, plus x. System.out.println, instance x, plus this.x. Public static void main, string args. Example equals new example. Example.display. Output. Local x, 20. Instance x, 10. Explanation. The local variable x in the display method shadows the instance variable x. The instance variable can still be accessed using this .x. Nested blocks and scope. In Java, you can have nested blocks, i.e., a block of code within another block. Variables declared in an outer block are accessible in the inner block, but not vice versa. Example of nested blocks. Public class example. Public void display. Int outer equals 10. Int inner equals 20. System.out.println, outer variable, plus outer. System.out.println, inner variable, plus inner. / uncommenting the following line will cause an error because inner is out of scope. / system.out.println, inner variable, plus inner. Public static void main, string args. Example equals new example. Example.display. Output. Outer variable, 10. Inner variable, 20. Explanation. Outer is accessible within the inner block, but inner is not accessible outside of its own block. Summary. Local scope, variables defined inside a method or block, accessible only within that method or block. Instance scope, variables associated with an object, accessible by all methods in the class. Class scope, static variables and methods, shared across all instances of the class and accessible without creating an object. Method scope, the scope within a method, where variables are local to the method. Understanding scope is essential for managing data visibility, avoiding naming conflicts, and controlling the lifetime of variables in your Java programs. 3. Java recursion. Recursion in Java is a programming technique where a method calls itself in order to solve a problem. Recursion is particularly useful for problems that can be divided into smaller, similar subproblems. The recursive method continues to call itself with different arguments until it reaches a base case, which is a condition that stops the recursion. Key concepts of recursion. Base case, the condition that stops the recursion. Without a base case, the recursion would continue indefinitely, leading to a stack overflow. Recursive case, the part of the method where the method calls itself with modified arguments, bringing it closer to the base case. Example of recursion, factorial calculation. The factorial of a non-negative integer nn is the product of all positive integers less than or equal to nnn. It is denoted as n, n, n. The recursive definition of a factorial is 0 equals 10 equals 10 equals 1, base case. N equals n times n1, n equals n / times n1, n equals n times n1. Recursive case. Recursive implementation of factorial. Public class recursion example. / recursive method to calculate factorial. Public static int factorial, int n. If n equals 0. Return 1, / base case, 0. Equals 1. Else. Return n plus factorial, n, 1, / recursive case. Public static void main, string args. Int number equals 5. Int result equals factorial, number. System.out.println, factorial of plus number plus is, plus result. Output. Factorial of 5 is, 120. Explanation. When factorial, 5, is called, it calculates 5 asterisk factorial, 4, and so on until it reaches factorial, 0, which returns 1. The results are then multiplied together as the recursion unwinds. Example of recursion, Fibonacci sequence. The Fibonacci sequence is a series of numbers where each number is the sum of the two preceding ones, usually starting with 0 and 1. The recursive definition is f 0 equals 0f 0 equals 0f 0 equals 0. F 1 equals 1f 1 equals 1f 1 equals 1. F n equals f n 1 plus f n 2 f n equals f n 1 plus f n 2 f n equals f n 1 plus f n 2 for n greater than or equal to 2n / 2n greater than or equal to 2. Recursive implementation of Fibonacci sequence. Public class Fibonacci example. / recursive method to calculate Fibonacci number. Public static int Fibonacci, int n. If n equals 0. Return 0, / base case, f, 0, equals 0. Else if n equals 1. Return 1, / base case, f, 1, equals 1. Else. Return Fibonacci, n, 1, plus Fibonacci, n, 2, / recursive case. Public static void main, string args. Int n equals 10. System.out.println, Fibonacci number at position plus n plus is, plus Fibonacci, n. Output. Fibonacci number at position 10 is, 55. Explanation. When Fibonacci, 10, is called, it calculates Fibonacci, 9, plus Fibonacci, 8, and so on until it reaches the base cases of Fibonacci, 1, and Fibonacci, 0. The results are added together as the recursion unwinds. Advantages of recursion. Simplicity. Recursive solutions are often simpler and easier to understand for problems that have a naturally recursive structure, such as tree traversal, searching, and sorting algorithms. Elegant solutions. Recursive methods can lead to elegant and concise solutions compared to iterative approaches. Disadvantages of recursion. Performance. Recursive methods can be less efficient than iterative methods because each recursive call adds a new frame to the call stack. This can lead to increased memory usage and potential stack overflow for deep recursions. Complexity. Recursive methods can be harder to debug and reason about, especially when the recursion depth is large. Tail recursion. Tail recursion is a special form of recursion where the recursive call is the last operation in the method. In languages that support tail call optimization, TCO, this can be optimized to avoid adding a new frame to the call stack, improving performance. However, Java does not optimize tail recursion, so tail recursive methods do not have a performance advantage over non-tail recursive methods. Example of tail recursion. Public class tail recursion example. // tail recursive method to calculate factorial. Public static int factorial tail, int n, int accumulator. If n equals 0. Return accumulator, / base case. Else. Return factorial tail, n, 1, n asterisk accumulator, / tail recursive call. Public static int factorial, int n. Return factorial tail, n, 1, / initial call with accumulator set to 1. Public static void main, string args. Int number equals 5. Int result equals factorial, number. System.out.println, factorial of plus number plus is, plus result. Output. Factorial of 5 is, 120. Explanation. The factorial tail method is tail recursive because the recursive call is the last operation in the method. The accumulator carries the result of the factorial calculation as the recursion progresses. Recursion versus iteration. Recursion is often more intuitive for problems with a recursive structure but can be less efficient due to the overhead of multiple method calls. Iteration typically uses loops, example for, while, and can be more efficient, but may result in more complex code for problems that are naturally recursive. When to use recursion. When the problem can be divided into similar sub-problems, such as with tree structures, fractals, and certain mathematical sequences. When an iterative solution is less intuitive or more complicated than a recursive solution. Conclusion. Recursion is a powerful tool in Java that can simplify the implementation of certain algorithms, especially those that naturally fit into a recursive pattern. However, it should be used judiciously, keeping in mind the potential for increased memory usage and stack overflow in cases of deep recursion. In Java, a class is a blueprint for creating objects. It defines a data type by bundling data, attributes or fields, and methods, functions, that operate on the data. Classes are the fundamental building blocks of object-oriented programming, OOP, in Java, enabling the creation of modular, reusable, and maintainable code. Components of a Java class. Fields, attributes, methods, constructors, blocks, nested classes. 1. Fields, attributes. Fields are variables declared within a class. They represent the state or characteristics of an object. Each object created from the class has its own copy of the fields. Example of fields. Public class person. / fields. String name. Int age. 2. Methods. Methods define the behavior of the objects created from the class. They can perform operations using the fields of the class and can be called on objects of the class. Example of methods. Public class person. String name. Int age. / method to display person details. Public void display. System.out.println, name, plus name. System.out.println, age, plus age. / method to update age. Public void set age, int new age. Age equals new age. 3. Constructors. Constructors are special methods that are called when an object is instantiated. They initialize the new object. A constructor has the same name as the class and does not have a return type. Example of constructors. Public class person. String name. Int age. / default constructor. Public person. Name equals unknown. Age equals 0. / parameterized constructor. Public person, string name, int age. This dot name equals name. This dot age equals age. For blocks. Blocks are used to initialize class fields or perform actions at the time of object creation. Instance initialization block runs every time an object is created. Static initialization block runs once when the class is loaded into memory. Example of blocks: public class person, string name, int age, / instance initialization block, system.out.println, instance block executed, / static initialization block, static, system.out.println, static block executed, / constructor, public person, string name, int age. This dot name equals name. This dot age equals age. Public static void main, string args. Person equals new person, Alice, 30. Output. Static block executed. Instance block executed. 5 nested classes. Java allows classes to be nested within other classes. Nested classes can be static or non-static. Static nested class belongs to the outer class and does not have access to instance variables and methods of the outer class. Inner class, non-static nested class that has access to the outer class's instance variables and methods. Local class, declared within a method and is accessible only within that method. Anonymous class, a local class without a name, used for creating one-off implementations. Example of nested classes: public class, outer class, / static nested class, static class, static nested class, void display, system.out.println, static nested class, / inner class, class inner class, void display, system.out.println, inner class, / method with local class, void method with local class, class local class, void display, system.out.println, local class, local class local equals new local class, local.display, / anonymous class, void method with anonymous class, runnable equals new runnable, @override, public void run, system.out.println, anonymous class, new thread, runnable, .start, public static void main, string args, outer class outer equals new outer class, / accessing static nested class, static nested class static nested equals new static nested class, static nested .display, / accessing inner class, outer class .inner class inner equals outer .new inner class, inner .display, / accessing local class, outer .method with local class, / accessing anonymous class, outer .method with anonymous class. Output. Ruby. Copy code. Static nested class, inner class, local class, anonymous class. Creating and using a class. To create and use a class, follow these steps. Define the class. Create a class definition with fields, methods, and constructors. Instantiate the class. Create objects of the class using the new keyword. Access members. Use dot notation to access fields and methods of the object. Example of creating and using a class. Public class car. String model. Int year. / constructor. Public car, string model, int year. This dot model equals model. This dot year equals year. / method to display car details. Public void display info. System.out.println, model, plus model. System.out.println, year, plus year. Public static void main, string args. / create an object of the car class. Car equals new car, Toyota Corolla, 2022. / access fields and methods. Car.displayInfo. Output. Model, Toyota Corolla. Year, 2022. Access modifiers. Java provides access modifiers to control the visibility of class members. Public, accessible from any other class. Private, accessible only within the class itself. Protected, accessible within the same package and by subclasses. Default, no modifier accessible only within the same package. Summary. Class, a blueprint for objects, defining their data and behavior. Fields, variables that hold the state of an object. Methods, functions that define the behavior of an object. Constructors, special methods used for initializing new objects. Blocks, used for initializing fields and performing actions at the time of object creation. Nested classes, classes defined within other classes, which can be static or non-static. Understanding classes and their components is fundamental to object-oriented programming in Java, enabling you to create modular, maintainable, and reusable code.